good morning, everyone. I'm Kristian Larsson. I am a network automation guy working for Deutsche Telekom within a project called TerraStream. And I'm here today to give you a talk on how to build a sweet setup for doing NSO development. I won't be talking much about sort of my background or what I'm doing now. Suffice to say, TerraStream is the fixed, so next generation design for Deutsche Telekom's fixed network. As part of that, we want to have the network completely automated, and that's the piece that I am working on. I have a bit more than an hour today, and despite that being quite a long slot, this is going to be quite fast-paced because I have a hell of a lot of slides. So I hope that you didn't stay up too long yesterday and had your coffee this morning. With that said, though, I do enjoy questions. I want this to be sort of interactive. So, I mean, if you have questions as we go through the presentation, please just ask them. I think it's better that you do it throughout, as we'll have, sort of the context fresh in memory and everything. Okay. So, you probably have a network to run. It might look something like this. We're all in this room together because you or someone else picked NSO to do the job of running that network. NSO is like it's a framework or a platform in which you write code, right, to do what you want. We have to do development. And to do development, we need development tools in and around NSO that are well suited to NSO. And that is the topic of my talk. Specifically, I will talk about two areas. It's testing, in particular in CI. We heard, or I picked up a couple of questions yesterday about how to do testing. This talk is for you. The second sort of area is tooling, just around the entire development process, as well as how we structure things in Git, and yeah, overall structure sort of. Might be a few words on deployments if we have time. But then we're also going to talk a lot about automation. And this is not automation of NSO doing something with the network, but this is automation of the development process itself. Unfortunately, I mean, it would be really nice if all the examples that I have, if that was available, in a Git repo that you could pull down and have a look at. Unfortunately, that's not the case. The configs that we have, I just can't share them. They're too specific to our environment to make sense to someone else, and they undoubtedly contain some secrets, and I simply don't have the time to clean it up. There are screenshots in here, so I think that you'll get enough information to be able to implement this on your own. And above all, I am logged into our system. I have the entire source code base on my laptop right here. So if you have any questions, please take this opportunity and we'll dig right through it. We can look at code together. And I mean, I'm here for you, right? But above all, I want this to sort of spark interest and give some inspiration for how you can improve your everyday NSO development environment. Does everyone know what a CI testing system is? One hand. Great. Can we have, how many people can raise their hand? Okay, baseline. How many people know what a CI testing system is? Ah, much better. Thank you. Okay. But a CI testing system can automatically run tests when you push code to your Git repo. We can, enforce that those tests must pass before you're able to merge the code to master or something like this. It's sort of like a quality control system, a gatekeeper preventing you from committing shitty code, at least if you got your tests sort of right. So we use GitLab and GitLab CI. That's what I will be sort of focusing on here, but it's applicable if you have something else like Jenkins as well, right? How many in here have a CI system for their NSO development today? Fewer. Okay. Okay, so let's dig into the first area then, namely testing. So why test? Lots of reasons to test. I won't go through all of it. I think that you're sort of in the you got this already, so it's more about how, right? But anyway, so I like to test my code because it helps me develop faster. So when you're writing a program, I mean, you're essentially evaluating its behavior in your head, right? And I think that's the sort of essence of programming. You have a wanted behavior, and you come up with some code that you evaluate in your head, and you're like, yeah, this fits, all right? Humans can typically get small pieces of code correct. This is why we write small functions. They're like a page long or something. We put this together into a larger program. And with a sufficiently large program, it becomes impossible to keep in your head. Right? If you change something somewhere, you cannot evaluate what that means for the entire program. And this is why we have tests. We have tests so that we can lock down wanted behavior of the program. We can make sure that it's doing the correct thing for some situations, right? So we can go ahead and change some other thing, but make sure that we're not breaking something inadvertently. So having tests it's not a jail, it's liberating. You can now let your brain focus on the right things. There is a certain threshold, a sort of initial investment you need to do in this typically to set up your test environment, write some initial tests that actually make sense. But I think once you've passed this threshold, it really does pay off, and it speeds up your development rather than slow it down. I've seen some small projects, they start out no testing, it works great just because it's small, right? The cost kind of becomes a bit higher the longer you wait. So I think do testing from the start. In fact, we now require tests. So in our environment, when we add new functionality into NSO, you must prove that that functionality works by adding tests or by modifying existing tests. So you should test. Okay. Back to our network. So our ultimate goal is to run a network, right? For the network to run, we have to push some configuration, and that's the job of NSO. Thus, a simple way of testing if NSO is pushing the correct configuration would be to capture the push configuration and then evaluate it somehow. Maybe the devices that you're using for your tests are actually NetSim devices, and we can sort of extract the configuration from there. And then I think the simple and naive approach to this would be to take those captured configuration and just compare them as sort of text files to an expected configuration. And maybe this is a good start, but I don't really think it measures up. So a word on NetSim, right? NetSim is nice. Does everyone know what NetSim is? Thank you. Don't make me baseline again. So it's Conf-D, right? Taylor's original product. It's imitating the northbound interface of a router, of a device. Like it can pretend to be an ISXR router or a Junos router by presenting a CLI or netconf interface or something else that looks just like the router. It's based on the same Yang models as you have in the NED, so it's sort of easy to set up, right? So with NetSim, we can put ISXR or Juniper configuration on something that looks like ISXR or Juniper, but it's really not. If you push an ISIS configuration to a NetSim device, you will never have an ISIS adjacency. So if you messed up the configuration somehow, if I put in the same router ID across all of my devices in my test bed, then I won't get some form of collision because there is no ISIS actually running, right? So it doesn't really show us the sort of errors that might pop up if we'd actually push this to a real network. So further using NetSim, since it's using the same Yang model as the NED, we're sort of locked into an echo chamber. I mean, you might think that you're testing interoperability with something else, but you're really not. I mean, you're testing NCS with sort of an NCS turned the other way around, and they're both using the same Yang model, so it's quite limited in that sense. But disregarding some of these challenges, I still think that NetSim does a reasonable job of testing sort of syntactic and maybe semantic correctness. But it doesn't prove that the configuration makes any sense. Just as there are millions and millions of stars in the observable universe, there are millions and millions of configuration permutations on any given network device. And just as most of these stars are host to no life, most possible configuration permutations are simply nonsensical. With Yang models, you know what the permissible value space is in a configuration. You know what you can configure. But this doesn't help you to prove that it actually makes sense. You can put a configuration that validates with Yang, that still doesn't make sense. You can configure, all the routing protocols on the same interface, and I mean that would typically be nonsensical in a production environment, right? So static analysis of configuration is hard. Yang might help you a bit, but it doesn't really go all the way. I think the better approach to testing your network configuration system is to use it to configure a network. Then you observe the state of that network and determine if it behaves according to your expectations or not. Here's an example topology with a bunch of different routers, a couple of different vendors, actually one of our sort of old testing topologies. All of them speak ISIs, and when connected in a topology like this, they will form ISIs adjacencies with each other. If we mess up the configuration for, let's say, Junos, Junos does not have ISIs authentication now, then we will see that there will be no ISIs adjacencies from Junos to the other routers, right? So NetSim is sort of a mocking, right? I think we really want emulation, so emulating the network. So if we want to configure and observe a network of routers, we're going to need routers like these, but they're expensive. Maybe you work for a rich incumbent network that has one of these, in which case you can go out and buy a lot of routers to fill your development lab with. And while I do work for an incumbent network, and maybe we have one of these, there's still not enough routers. I think our lab is probably larger than most other labs. There are probably a router for every member of my team in that lab. However, that's not enough. I want a topology of 10 router, and so does the developer next to me. So there are just not enough routers. This is, of course, where the cloud comes in. As everything else these days, you can virtualize routers. So you can run them in a cloud or just virtualized on a PC. So virtual routers are cheap enough to give every developer a good-sized topology to play around with. The cost is mostly in CPU and RAM, right? And that's like orders of magnitude cheaper than going out and buying real physical routers. So I'll get back to the actual details of running virtual routers, but for now, let's just pretend it's something that we have. Which brings us to the next sort of topic. So if we have this network, how do we configure and then observe the state of it? How do we observe state? We can get data from devices using a netconf, of course. We have SNMP, maybe CLI. Does anyone know of a good system able to do that? Of course, why we're here. NSO is that system. A lot of people just use it to configure things, but it's also able to fetch state from your devices. It's available under something called the live status node, in the devices something, and then live status inside of your NCS instance. Does anyone recognize this? Some. Great. This is a self-test function. It is a piece of skeleton code that you get when you run NCS make package. The idea behind a self-test action is that for every service that you define in NCS, there is also a self-test action. So services aren't just about pushing configuration, they're just as much about retrieving state from the network, evaluating that state, and making sure that it measures up to expectations. And I mean, this is just like a network device, right? I mean, if you configure a BGP neighbor on a router, you also expect to be able to retrieve some state about that. Is the BGP neighbor actually up, right? It's not a black box that where you can't see anything. You want to be able to retrieve state. So it's the same thing for NCS. You configure a service. Now you want to know, is the service healthy or not? And if any of this starts to sound like network monitoring, it's probably because it is. This is network monitoring. And I think that there's a problem in the way that most service providers organize themselves around this. There's a form of compartmentalization going on. Configuration, provisioning gets to live in one corner of the network, of the company, whereas monitoring is on the other side, and in between you sort of have the network operations people. They sit over here, look in the monitor system, see, oh, this is a problem over here, and then well, I'm going to go over the configuration system over here and fix it. It's the swivel chair. Carl used to talk about that. Configuration monitoring actually goes hand in hand, and I think that services that we build in NCS needs to, NSO, sorry, they need to consider both. That I also mentioned that everything that we do are constructed as services. So forget about all the other ways you can use NSO. I think you should use services. It's a great abstraction layer, and so use it to manage all of your configuration as well as monitoring of these services. This is an example from one of our services. It's very small. It's called the BGP customer. It essentially just tells us if the BGP peer is up or not, but there's some metadata around this. I'll talk more about how self-test looks later on. But what's really nice about the self-test is that you can use them both for monitoring services for the purpose of CI testing, as well as for monitoring a production network. It's the exact same self-test. So normally when you write tests for a CI environment, you end up doing just that. You write it for CI and then you throw it away. It's not used in production. But using these self-tests, I mean, they're shipped inside of NSO, right? Your NSO sort of package. So whenever you deploy that somewhere, you can use it there to monitor things, both in production as well as in CI. I mean, some clever people at Tail have already thought this through, right? Which is, of course, why it's in the skeleton. But I don't think that many people actually make use of it. So I strongly recommend that you do and minimize the amount of test duplication between your CI test and your normal network monitoring. So this is sort of the foundation of our testing. Virtual routers for CI testing, it's local development as well, I'm going to talk about that. And then self-test, that's how we test this thing, right? So self-test on every NSO service. Configuration and monitoring, they belong together. Remember this. And of course, it's all exposed on the same API, right? Which makes it really, really nice. I mean, it's not nice to your customer if you say, oh, you go and configure it over here. Oh, you want to monitor? Okay, you have to go over here and look at it, right? I mean, that doesn't make any sense. So NSO service self-test is not the only type of testing that we have. You probably heard of unit testing. And we do use them for specific things. I mean, it's great to test small units of code, right? The downside with them is, just as this picture illustrates, it's so easy to miss the big picture. You have your unit test, it's testing something very specific, it's passing, of course, but the whole ship is sinking. I think it's only like of sort of the aerospace industry that's probably able to afford, they have the budget to cover their whole thing, do more formal testing or whatever of their entire system. The rest of us just don't have the budget. So what do? Functional testing, right? It's more of an end-to-end thing. We look at it as I mean, you can call it a black box or whatever. You don't care about the inside. A unit test looks at the inside of your code, right? It's aware sort of internals. But here we back out and say we tested the whole system as a function, or in this case, actually, the whole network, right? And with just a few tests, we can sort of cover the whole thing. The problem with it is, of course, that it doesn't return as detailed error messages as a unit test. As an example, we spin up that network topology, right? If we run a ping across that network, we're able to infer that, you know, if the ping works, then interfaces must be configured correctly. We must have an IGP up and the BGP is up. Our route policies must be doing something right, or else the ping would never work. On the contrary, then, when it's not working, we have no idea in which area the problem is. So what you want to do is, I mean, let tests complement each other, right? I mean, we have self-tests that can prove that individual interfaces, BGP sessions, etc., are working, and then you use an end-to-end test to prove that the whole thing is actually working, right? And I think that, so it's a very cost-effective way of doing testing. So yeah, let tests types, methods complement each other. Before we look more at I'm going to show how we do testing right now, but before we get to that, I have to talk a little bit about how we ship NSO, and that's containers. So we use containers, specifically Docker containers, to package up NSO into something that is deployable. I think Docker is quite nice. It's one of those examples of where the whole is greater than the sum of the parts, right? Or is it? There's like nothing magic in there. It's just, you know, some basic fundamental building blocks, but they put it together into a very nice package that it just solves sort of practical problems that we have. Container images are immutable, which just means they can't change, right? So what we do, our process here is sort of we compile our code once, we build the container once, we package it up, And then we use that specific container image in our testing. And once it's past testing, we can then push it to production. So it's the same image. We don't rebuild it ever. It's not a complete guarantee against all sorts of bugs, but I think this is a very good start. And I mean, doing it like this, we never recompile, right? So let's just say you had one of those weird compiler bugs, you'd actually be able to catch it, right? Because it's the exact same binary output that you're testing that you're also pushing into production. It's also super convenient because this image, we can use it in production, in CI testing. If you want to have your own little playground environment of our NSO instance, then you can do that. You just take this image and spin it up on your laptop or elsewhere. Okay, so now that we have sort of the environmental foundation in a network topology of virtual routers, we have an understanding of what kind of tests we want to run against this network topology. Let's look at how it comes together. How many in here have seen GitLab and GitLab CI? Okay, a few, thank you. So this is a CI pipeline. This shows the CI, yeah, it's a CI pipeline. So these 4 columns that we have here, these are called stages. In each stage, there are multiple jobs. All the jobs in one stage are executed in parallel, provided you have enough hardware to run it. And all the jobs in one stage must succeed before we can proceed to the next stage, unless you can mark a job explicitly to allow failure of it. If we start on the left, this starts on the left, the build stage up there, it has 2 jobs. The first is called build. If you have hawk eyes, you might be able to see that. That is the most important job. The thing I just talked about, building a Docker container, that is what it does. The output of the build job is a Docker image. And that's really all that is passed from the first stage of this to the second stage. There's a second job there in the build stage. It's check up to, this is just check some dependencies that they're up to date. That's not important. So what is important is sort of the next column here is the test stage, right? This is where all the interesting stuff happens. All the things I just talked about, all the virtual routers that we spin up, all the sort of testing that we do, that's what happens in this column. Each and every one of these jobs will spin up a virtual network. It will spin up an NSO instance, at least one NSO instance, and then it will perform testing on that. So that's a heck of a lot of virtual routers that are being spun up. And it's a few big, I mean, you can get one of these big servers, right, like 40 cores, hundreds of gigs of RAM or something and to run this. We have a couple of those. But they're quite cheap, right? Can you see the names of the jobs? Yeah, good. So we have organized our tests into something I call the test suite. So if we look at the jobs here, test BGP SROS, test BGP VMX, and test BGP XRV. These are 3 platform instantiations of the same test suite. It's the test BGP test suite. And this is a very nice structure. So the test suite defines the network topology, the addressing that you use in there, and then in the platform instantiation, you just change some minor details like interface names, because those are specific to the platform, right? But apart from that, everything is common in this test suite. So that makes the cost of having multiple platforms is very, very low. Makes it easy to test for 3 platforms or 4 or 5 or 6, right? Because you only define the test once. When we started out, we had it differently. We had a much bigger topology. We had a mix of vendors in that same topology. But if we wanted to do the same sort of test across 3 different routers, we actually had to implement 3 different tests. This is because the Juniper router would have one IP address, the Cisco would have another, and the Nokia would have yet another, because they're in the same topology, right? So they need to have unique addresses. But with this, all the different jobs are utilizing the same address space because they're running isolated from each other, right? So it makes it very easy. The test definitions, you only need to define it once, and then you can reuse it for all the platforms. So I can strongly recommend building it up like this. Of course, you want to do testing with multiple vendors in the same test topology as well, right? And I mean, that is something that we're going to come back to that. I mean, we're sort of coming full circle again, right? But we started out with having a mix, then we're going to the single, and then I'm going to get that back in there. But without, we're going to avoid having to write tests multiple times, right? This whole CI pipeline takes something like half an hour to run, which, given the amount of routers in here, I think is quite nice, actually. I mean, it's quite relatively fast. I know it's not fast enough, sort of, but let's get later to how we actually do development, right? Okay, so we're gonna okay. This was suboptimal. Sorry, I'm not too used to having multiple screens. It's so difficult to look at very long text output in a static presentation, so I prefer to do it in a web browser. So this is our actual test, our actual GitLab instance. Okay, so I don't know if you've seen one of these jobs. So there's some startup stuff, happening, setting up the test job and everything, right? We're pulling in a few things. And then we sort of down here, we start to get to the interesting bits. Our whole tests setup and configuration and all of this is orchestrated by makefiles, because I like makefiles. I think they're excellent for something like this. We start here by spinning up our topology. So the make-c, right, we're telling it in the, is the sound working? Test CI, and then the test suite, and then the platform. These are fed into the CI job as environmental variables, right? So they're variables in here. So we have the test suite, and then the platform, and then we tell it start. And that's the point where it's going to start up these routers. The routers themselves are Docker images. We're going to get to that. So it pulls down a bunch of things, and then here we're going to see how it starts them up. Container, CI, blah, 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 doesn't exist, starting it. And this is the Docker container, it's some UUID, something of how it starts it up, and then it starts up all these different instances. So it's a quite big sort of topology that we get here. Run netsim for this particular topology. There are no netsim jobs. Then we also tell it to start up NCS. There are also some supporting containers like an InfluxDB and Grafana. And then we come to the next make target. In this case, it's the same test suite and platform that we're working on, right? I mean, in this case, you can see it's BGP. The test suite is called BGP, and the platform is VMX. We tell it to run configure. So the configure job here will tell NCS, it will load up configuration into NCS, and NCS will in turn configure our little virtual network. So there's a bunch of different configuration files. It's copying these into the container, and then it's executing commands inside of NCS that's running in the container to load these. So configure, load merge, /NCS config terrastream, right? And then it commits. So here we can see how the NCS instance we have in there, it starts committing these things, right? Also doing some package reloads and stuff. Here we get to the interesting bits. More loading of configuration. Show devices brief. These are the devices in this test, right? That we loaded up into NCS. There are two NCS instances in this particular test. So the other one is called other NCS. And then we get to testing. We use reactive services. So the first thing that we're going to do is check that our reactive services are done. I'm not sure if you're familiar with them, but they have a finite state machine. It's a plan, and it has a ready state. It's the final state. So we look here, before we continue to any other test, we want to make sure that we configured everything, right? So we look at show infrastructure. This is our own node. This is where we sort of keep our stuff, right? Infrastructure device, blah, blah, blah. Plan, and then the component self, the state should be ready. Or we look at the ready state, right? And then get the status of that. Status reached. So we're all good in this case. We're done here. We can proceed. It's quite a lot of this stuff. I'm going to sort of skip ahead to where we get to the more interesting things. Here's one. Backbone interface is one of our services. In our backbone network, you have interfaces, you have links connected to each other. Backbone interface is a service that configures these. So here's the instance on this router, on this interface. I mean, you recognize this. This is on a Juniper box, right? I mean, we're in the VMX test suite. Then run the self-test function or action. And this is the data we get back. It's split up into these different sections. We have one on the interface itself. There's one on ISIS because we run ISIS, and there's one on PIM. And it returns all sort of data in here. And this is what we use essentially to tell you, is this service instance working correctly or not? It continues like this. There are quite a lot of interfaces in here, so it's a long list. You can also, the nice thing is sort of in NCS, right, is that you can look at some of this information in a more summarized fashion, like this. Here you have a table looking at all the instances, right, and just one single leaf, the success leaf. The different services you have, the self-test, the data that it returns, right, is going to be service-specific. But we have nodes in there that are common to all services. It's actually in the skeleton code, right, that you have a success leaf and then there's a message. We've kept this success leaf. So all the services we have this success leaf. This is very nice because you can potentially crawl the Yang model, find all the self-test action, then you just pull all these actions and then you look at the success leaf and all of them says true. That means all the services in your network are working correctly. It's a very good chance your network is up and running, right? If any of them says false, then you might want to start looking into the details of why that might be. But I think it's nice sticking to having some of the values returned always be common so that it's easy to understand for everyone. And then, yeah, it just continues. You can also display it in JSON. There are lots of tests in here. I'm not going to go through all of it. I don't think we have time. But I mean, if you have questions, please shoot. So at the end, here we have some failing. You can just have a look at this, right? So you see eBGP, blah, blah, self-test, success false, and then the whole, we just wait a bit, we retry the self-test, and after a bit, we see if it succeeds or not, and I think it does a bit later down in here. Oh yeah, it sort of flipped over. So 24 seconds elapsed, we retried, and then all of them are success true instead. Here at the end, we have a different test suite. This is where we do other sort of testing, not the self-test in NCS. In this topology, in the BGP test suite, we have all of these BGP speakers that are surrounding some of our routers, and we set up BGP sessions, we announce routes, and then we look at the routes that are advertised back to us, and we evaluate that. So we're checking that our BGP routing policy is working correctly, and these are the tests for that. So we can look at this one, for example, test BGP 1101. Peer 1 should see customer 1 and customer 2. Okay. So it verifies that it actually sees those prefixes in BGP. The first tests here are actually, I should have picked another platform. So ACLs are not implemented on VMX for this particular test. They are on other platforms. So what we're doing here is testing that our ACLs are functioning properly by sending test packets across. So we're checking the data plane of this little test topology, making sure that the ACLs are working correctly. Just not on this platform. Here at the end, we're sort of doing, we want to make sure that our services that we just can't configure them, but that we can also remove them, right? So, and we want to make sure that they're stable. And by stable, I mean if you push something and then you do a sync from, and then you do a check sync on a service, will that service then say, you know, I want to change something? Or is it stable, right? So if you have unstable services and you try to start running reactive services, you might end up with problems, sort of. Or it depends on what you're doing. But for us, it's a problem. We can end up with infinite loops, essentially, because of this, where NCS will just sit there chugging along, doing sync from and then redeploy of services. So we're sort of doing a test of this, checking are services stable or not, and then we're doing a test in actually removing services, so we're making sure that that also works. And I mean, we've seen cases where like the NED, in particular CLI NEDs, you're provisioning something where it's just fine, but then when you're trying to remove it, the NED does it in the wrong order, and bam, it doesn't work, right? And it's sort of embarrassing. When you're just testing everything in CI, you're just configuring everything works, and then someone does it in production. It's like, oh, I wanted to remove this service, and you can't actually remove it. That's sort of bad. Okay, blah 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 blah, and then here at the end, we can sort of see how it starts cleaning up the containers, all those virtual routers, all the NCS instances. It's shutting them down. That's what it's doing right here. And at the very end, we have uploading artifacts. So it's uploading a bunch of artifacts. We collect the logs of the NCS instances running in here. We collect logs of the routers and the configuration at various stages. Like before we apply some configuration, we save a dump as an artifact. After we apply some other configuration, we save a dump. Most of the self-test output is saved as in these artifacts as well. Okay. So one of the typical things that I've sort of observed in service, I've worked in a service provider business for quite some time, at service providers, right? So typical service providers environment have vendors come in and do a proof of concept of something. The proof of concept involves building up a sort of a lab environment, and you do some testing of that, and then you buy the thing, and then you deploy it in your network, right? The problem with this is that once you bought it, you don't have the lab anymore. It's typically torn down. And ever after, you're afraid of doing changes because the vendor came up with the configuration in the first place, and now you're sort of locked into that, and you won't change it. So what I'm suggesting here, right, with this virtual network topology, what you're doing is you're sort of building a virtual copy of your own network. And with that, you can test many times as you do changes. So I think that's really nice. It increases your confidence in what you're building. Yesterday, everyone wanted greenfield. I think you can use CI as your greenfield. It's not a perfect drop-in replacement for having an actual production network being built greenfield, but it's a pretty good substitute. It takes a long way. So in CI, you can deploy 1,000 times. You can gain confidence in what you're doing and seeing it actually working with virtual routers. And then when you're doing the production environment, you have a little bit more confidence in what you're doing, sort of. That's my recommendation. So I mentioned this before, right? It takes like half an hour for our test. If there are multiple of them running in parallel, it's going to take longer. If you threw more hardware, maybe it'll run a little faster. If there are no failures, all the planets align, maybe it's a little bit faster as well, right? But long CI test time is essentially boring. When you're doing development, I think it's very important that you don't include the CI testing in your sort of normal development loop. So when you're developing, I don't know how you develop, but I typically go and change some code, then I reload that in NCS, and then I want to see it work, right? So it's sort of this loop. And that needs to be sort of fast. You can't send this to the CI system every time and wait 30 minutes for it to, and that, oh, I missed this thing, right? So what you want is local development. That is the solution to this. Most of the startup time here, we just need to do that once for local development. We start up our virtual router topology. It takes 5 minutes to do that, and after that, you change your code, you do a reload. It takes like 20 seconds to reload packages in NCS if you have a lot of them like we do. or you don't reload Yang models, it'll be a little bit faster. And so the whole that whole sort of cycle is in tens of seconds instead. And I think that's a much better outset for being a development environment. And having your own test network for development is crucial in this, because you can make changes. You don't need to synchronize with anyone else. You know, are you doing changes to the lab network right now? Can I go ahead and do things, right? So I think it's crucial that you have your own. When constructing or building an environment like this that you want to run in CI, it's crucial that you build it in such a way that you can also use it for local development. It can't be different code paths. Like all the make files that are setting this thing up, it needs to be the same for when you're doing local development and for when you're doing CI, because that makes it easy, right? So all the make targets that I just showed, the make start, make configure, and then make test, all of these can be run locally. I have a Mac. Mac doesn't support KVM. All the virtual routers need KVM, so I can't run it on this laptop. But if you have a proper laptop that could run Linux, then you can run our virtual router topology on your laptop. Of course, you can't run all those topologies, all those jobs sort of at the same time, because that consumes a couple of hundred gigs of RAM. But if you have a laptop with 16 or 32 gig RAM, which is you know, perfectly reasonable these days, then you can at least run one of these topologies. Right, so like we talked about before, it's virtual routers, right? We're gonna get into the details of how we run them. This is what I just talked about. It's not just in CI, it's for local development too. And see here. How the hell? Can someone proficient in Mac help me move a window from one screen to another? Huh? I don't know where the other screen is, sort of. Oh, here it is. Thank you. Silly. Okay. Like I said, I have a Mac. It doesn't work on this thing. So I've cheated, right? I've logged into a machine somewhere else. This is a little shell script that we have to help us start under the hood. It's actually running those make files. In addition to running the make files, it also takes care of compiling our entire NCS packages and building a Docker container out of that. So it's start playground. I want to use it in dev mode, which means it loads up local packages. I use a topology. Just like I explained, right? We have test suites and platform instantiations of that. In this case, I'm going to take a BGP and then the XRV platform. I tell it non-interactive because I don't want to be asked any questions while this is working. So it's going to do some compilations, and while it's doing that, I'm going to talk some more. We'll get back to that, of course. That's the whole point, but we don't need to be looking at it. So most vendors provide a virtual router. These days, and you can potentially use, physical routers as well. I mean, we talked about this a little bit, right? But I mean, it's sort of cumbersome to do that. You have to reset your router between every test run. You probably have a limited amount of them. So if you want to do testing in parallel, if you want to test large topologies, it's just much easier to use virtual routers. So you get that concurrency. You can just destroy them when you're done with the testing, regardless if it failed or succeeded. You just destroy them, and then when you start a new test, you just start from scratch. You spin them up. There's quite a few routers sort of available from different vendors. I just picked a few of them and wrote them down here. So what usually happens is that you get something like a VMDK, an ISO, QCOW file from these, or multiple of them, and then there might be some startup scripts. When you start them up, you might have to provide different sort of interfaces. It might be virt.io, it's E1000 NICs, or something else. So while it's very nice with virtual routers, just setting up an environment with them can actually be quite sort of manual, cumbersome, lots of things to consider. And you know, so setting up a large environment with all sorts of different kinds of routers is a heck of a lot of work. And this is where VRNet Lab enters the picture. So this is a system that I wrote a couple of years ago. It's very loosely based on something else that I wrote, a previous internal project, but that had various shortcomings, and I did a complete redesign. And VRNet Lab is that redesign. So this time around, I decided to put it in Docker containers. So it still uses KVM. So it's KVM running inside of Docker containers. Docker is used foremost as a packaging format, so we can ship things as a single unit. If you have all those VM images and startup scripts and all those things, right, we don't want to ship them around as loose files. Docker provides an excellent solution for us, so it's sort of done in a single piece. There's already Docker repositories, things like this, right? So we don't need to take care of that piece. It's handled for us by Docker already. These boxes, they need to be bootstrapped. Depending on which sort of box it is, it happens in a few different ways, right? VRNet Lab takes care of that for us. So what we're going to end up with is a router that's started. It has some IP connectivity. It runs SSH and netconf, and there's a user created in the system. And this is just what we need, coincidentally, for talking to it from NCS, right? We want the device to have netconf, it needs an IP address, and we need to have some credentials so we can log into it. And VRNet Lab provides just that. So above all, it's very simple to use. This last thing here is a command line to actually start this thing out. We do docker run. We have to tell it privilege. This enables KVM hardware acceleration. If you don't do that, it's going to be very, very slow. Dash is D is for daemon, put it in the background, and then the name of the Docker image, vrxrv533 in this case. It's an old slide. We're using something newer now. All the various vendor routers all have the same interface. It doesn't matter if it's XRV or if it's VMX, it still looks the same when you're starting it up. We're going to go through this very quickly. So inside, I just want to show you sort of how it avoids or hides all of this complexity. If you look at something like the VMX, there are actually two virtual machines in there. You have the VCP, which is the control plane. You have the VFPC, which is your forwarding plane. And all of this is running in there. They're connected through a Linux bridge called brint, but since this is in a namespace, a container namespace, it doesn't matter. We can still spin up many of these on the same computer, and they won't collide with each other. There's a launch script in there that handles launching this whole thing, and I think it's a heck of a lot easier to read that launch script than it is reading the startup script that come along with a normal VMX installation. I'm not sure if you looked at those, but don't. You'll claw your eyes out after. So it's very easy to use, and it just handles all of these things. It's perfect if all you want to do is have some virtual routers to test your NCS installation with. Just a word on the networking part of this. So we're actually building our own overlay network with this, which gives us sort of very flexible networking. We rely on the underlying Docker network to connect them together, but then create these virtual links in between. So in this case, we have two of these VRNet Lab containers up there, and VRXCon is another container that connects them together, and we form this virtual link between the two first interfaces of this. VRNet Lab doesn't support all virtual routers out there. You have to you have to write the launch script and stuff. This is roughly what's supported today. We use the ones in bold, so XRV, a beta version of Huawei VRP, VMX, VQFX, and Nokia VSR. How am I on time? Oh, we're going to skip a little bit on the topology. There's a nice way to define the topology that you use inside of VRNet Lab. It also helps you start up the containers with the correct topology. A very important aspect of using VRNet Lab is that the configuration for the virtual network topology can also be kept together with your code in your Git repository. We didn't do this before. If you have something like a physical lab, then the topology is obviously outside of the control of the Git repo, right? You can't change a file in the Git repo and have your physical lab be rearranged automatically. That doesn't work. But with this, we have the topology definition together with our code, which is, you want that. OK. So with all that behind us, we can now hopefully look at the playground environment. It hasn't started yet, but it is. So I spoke too fast. Let's not waste time waiting for that. We can come back to it later, and we can look at some of the things there. Right? I'll just in the meantime, we're going to continue with the next section. Okay. So how to run CI tests, right? I mean, what we just saw. How does that actually work under the hood? So normally in a CI test environment, you're sort of constrained, or you have this low privilege mode, right? GitLab CI has a Docker runner, which per default means that every job is run in a new Docker container. It guarantees a fresh, clean start, and it's isolated from everything else, which is super nice. But when we want to run these virtual routers, which are containers themselves, we want to be able to spawn these. So how do we run that? If we're still locked down into this isolated little container for our test, we can't really do that. Docker in Docker, you might think, nah, you don't really want to go there, trust me. What we do, we sort of cheat. We consider our system be sort of a trusted system. So we break some of these low privilege stuff and just hand out more privileges to the container that's running the test. I've tried to illustrate this here. It's sort of mind-bending if you haven't worked a lot with this. It's sort of difficult to grasp, but I've done my best trying here. So GitLab up to the left is your, that's where you have your code, right? Something happens there, you push a commit, and this is of course then going to trigger a CI run. So commit up there, it talks to, should I explain, CI runner here, this is the physical machine, the gray one, right? We could have many of these running our test. On top of that is CI, that's the program, the GitLab CI runner, right? That talks to the main GitLab server and asks it, do you have any new CI jobs to run? And then it will pick one and it will start running it, right? We also have the Docker engine running here, which is what's running our containers. And I've drawn in the control socket, and we'll come to that. So commit, CI will pick this job up. It will then spawn a container which runs the CI job. So what we do here is that container has access to the control socket of the Docker engine. So it, in turn, can start up new containers. Sort of sibling containers in this case. And that is how we start up these virtual routers. The magic that you need in your CI runner config, if you've set up GitLab CI, I mean, this is part of your configuration, is that last line, volumes, var run docker socket. That's your control socket to Docker. So that's what you need to share with the Docker containers for them to be able to start up sibling containers. Okay. How to write a self-test. So there are a couple of different steps to this. It's all fairly simple. We fetch some data from the device, like the ISIs adjacencies on an interface. There's an optional step in here in mangling the data. It's something that we do. So we sort of translate the data. When you have all sorts of different vendors, we translate it into a vendor-neutral format of our own liking. After that, we evaluate that data. In the case of what I just shown you, the backbone interface self-test, that means we check, do we have an ISIs adjacency? Yes. Do we have exactly one? Yes. Is it the correct one? I mean, it should match up with some name, right? And then you do output. You write the output somewhere. Just want to mention, so fetching state, ISXR, native netconf, has pretty good support for this. That's what we're using, and we've been using it for quite long. We used to have beta builds from Cisco on 5.1, 5.3, which include lots of netconf. Now there's 6 something, and all of it sort of includes a pretty good native netconf interface. And it has, the YAMLs have good coverage for a lot of things, right? Junos has these RPCs instead. It's a little weird, but it works most of the time. Huawei, so if you have a really recent version of VRP 8, you have a netconf interface on there, but it's a sort of a hit and miss. They're doing some things correctly, but a lot of other things are not working correctly, unfortunately. Nokia SROS version 16 looks very promising, but it's missing something called well, support for content match and selection nodes in netconf get queries at the same time, which makes it actually impossible to use with NCS today. This will be fixed later this year. So version 16.1, I think, November. Live status. I don't know if you have ever. How many have looked? Are you fetching live status data today? Hands up. Interesting. Good. Thank you. Okay. So here's an example, right? Show devices, device, and then the name of the device. Live status. All the live status data, all the state lives under that node, right? And then on this is an XR router. We have ISIs, instances, instance, TS, that's for TerraStream, and then we fetch the neighbors, right? And this one only it only has a single neighbor, and that's what we can see here, right? So this is what this could look like in the CLI of NCS. And here's instead one of our self-test functions, right? So for ISXR, we check if the OS has ISXR, we fetch this sort of information. You can see there are some workarounds in here. But this is essentially what you need to do. Let's not talk. Yeah, I have to proceed. The output that we have of our self-test, this is the same we looked at before, right? Looking at the CI output. This is sort of vendor neutral, so it doesn't matter if you have a Juniper router or a Cisco router, it's going to look the same. It's sort of a leaky because the interface identifiers are box specific, right? But apart from that, all the other output is vendor neutral. We also keep a cached version of this. So when you run the self-test, it's not just going to output it to you, but it's also going to write it to /state under that service. And I think this has proven to be very, very nice. The cache data is very fast to retrieve from NCS. So when you have lots of instances, you can easily do this and look at all of them together, right? In this case, I'm doing display XML, so we did an XML. If you like XML. And we can also see the success leaves. I think I forgot to mention one thing before, right? So these sort of sections, the interface, the ISIs, and PIM, they also have a success leaf, right? So all of the individual sort of components in the self-test, they need to succeed for the total test to succeed. Yeah, I don't have a cursor. I hope you can see it. But it's very nice having this sort of cache data because it's very fast to retrieve. We have some metadata on when. You can see here at the bottom, last update, last poll duration. So you have some metadata about when this was retrieved from the network, so you know if it's outdated or not. Most of the time, you don't care if it's a couple of seconds or even a couple of minutes old. Other times, if you're doing a change to the network, you want to know that the data that you retrieve is fresh. If you got cache data that was from before you did the changes, you're going to see, oh, look, everything works right. Well, in practice, you actually broke something. Okay. Let's see if... Okay, this was weird. I'm not sure how to resize this because this doesn't have a normal bar. So it's a little weird. The bottom goes outside of the screen, but I'm going to try to do things here anyway, just to show you. So we just started up the BGP XRV environment. So from here, we can do like this, Docker PS. Look at the different virtual routers that are part of this. This is it. Unfortunately, we have line breaks here, but it's one for each. Here, this column is the name of it, so we can see this is one NCS instance, another one. The names here are given with my username. It's playground BGP. If you look in the CI environment, instead it says CI and then the pipeline ID. And then we have a bunch of different BGP speakers, and somewhere we're going to have the routers. These are the routers: XRV 276, R21, R22, R21, and so forth. And these are XRV routers 6221T. We can log into one of these. There's tab completion here as well, something you get for free with makefiles. Use makefiles. So make console 276 R1 5, like this. Now I'm on the console of the virtual router. So I can do things here. Make NCS CLI. This will instead give me login to my NCS instance, right? And from here I can, look at the devices that I have. I think it configured some backbone interfaces for me, so we can look at that. Can't see what I'm doing. I managed to run the self-test, as you can see. So now we actually ran this. We ran the self-test in the virtual network topology that I just set up for us. I don't think I plan really to show anything more, but if there are questions on this, I'm happy to do something else. Go. Yeah, so, yes. Oh, do you want to? Okay, I'll just repeat the question. So the question is, do you have anything more lightweight than starting up another virtual router for doing BGP testing? Yes. So part of VRNet Lab, there's a container called VRBGP. That is a normal container. It doesn't spin up a VM inside of the container. So it's more of a normal container. And in there, we run an instance of ExaBGP. And I hacked together a very ugly little API for that thing. So you can tell it, announce routes, what are the received routes, is your BGP neighbor up. So that is what we're using to test this. So all those, I'm going to exit from this thing. These ones, KLL pair on BGP XRE. BGP, so this is one of the BGP speakers. This one is called Tran2. That's a transit number 2. And that one is of this type. It is a VRBGP. So it is very lightweight. So yes. Unfortunately, I don't think we have time to go through the BGP testing, but maybe we'll see at the end. Okay, so let's talk a little bit about a structure we have for Git repositories related to NSO. This is what it looks like. NSO TS on the right here. Wait, there we go. Highlighted in greenish. This is our main repository. It contains all of our code from NSO services. It holds various utilities, some sparse documentation, CI testing scripts, and so forth. Having a single repository is really nice. Since CI tests are triggered on pushes to your repository, if you have a single one, it becomes impossible to commit broken code, right? Because CI will prevent that. However, as shown, we don't have a single repository, we have multiples. Here on the side, these are the NEDs that we have. Each NED is kept in its own repository, including both the NEDs that we produce as well as the ones that we get from Cisco. And having a repository per NED allows us to easily track them individually, which is a natural fit to how they are being released from upstream, right? So I just said it's highly beneficial to use a single one, but there's also other benefits to using multiple repositories. Makes it sort of useful. We actually started out having just a single repository, but we moved away from it because initially I think it was due to the long compilation times. Like all these NEDs, it would take 20, 30 minutes to start this thing up, which didn't make for much of a fun CIA experience. So when we sort of separated them out, the NEDs don't move that much, right? You don't have that many commits on them. So you can compile them a few times, and then when you're doing your main repository where you have a lot of commits, you're just relying on fetching already built binaries, right? But long compilation time wasn't the only reason. What we did before with a single repository, then upgrading the NEDs would be sort of tricky. If we had local changes, it would be even trickier. So to solve all of that, this is what we set up, having a single repository per NED. Finally, there's the Cisco NSO repository, which, much like the NEDs, is its own repository, and it contains NSO just as released from Cisco. That's the name. This is different from the NED repos that output binary artifacts. This one instead outputs a Docker image. It's a Docker image that we then base our work upon. So we take that, we add all the NEDs in the NSO's repo, we compile our own service packages, we add those in, and out comes our final output, which is a Docker image, right? The NED build, if you look at that, each NED compiles itself in CI for the specified versions of NSO that we've listed, and saves the binaries as artifacts. So NSO TS, that repo down here, it then pulls in the binary artifacts for the given version of NSO that we're using. We're compiling them for multiple versions of NSO because we want to be able to test with multiple versions of NSO. And I'll get to that later. So here's an actual CI pipeline for NED. There's a test stage on the left here, right? 2 jobs, one for 455, one for 461. And there's a second stage, which I'll get to. So these jobs, they compile the NED, and then they load it up into NCS. And that is what our tests currently consist of. It's sort of just a basic check, right? If you can't load it in NCS, then there's a, or if you can't compile it, then there's a big problem with it, right? Here's the CI configuration for that. This is what we actually do in CI for one of these things. So this is YAML, and the interesting bit happens in the script part there in the middle. This is just executed in a shell, in a bash shell, right? So first we source the NCS shell script. We start up NCS. We create a symbolic link from our own directory into packages. This is how we load ourselves. I mean, we are a NED in this case, right? Then we actually compile the NED, make in source, and then we do a little dance here to reload packages and look at the output of reloading packages. So we tell NCS to reload right, and if it can load up this package, we know it's doing something right. And at the end, we have the artifact statement telling it what should we be saving as artifacts, right, if the job succeeds. So this is what an actual run could look like. Just like the configuration, we source the NCS shell file, right? Then we start NCS. We have the symbolic link. Then we run make. Hell of a lot of output here from the compilation. We're going to skip all of that. Go to the next piece. We're doing the reload. A bit of a dance here for checking if that works out okay. And then it all did. So we're going to upload artifacts. And finally, the job succeeded. All right? So at this point, we've compiled and put out binary artifacts. So coming back to all of this integrates, one of the problems with having these multiple interdependent repositories is that changes to one repo can have effects on another repository, at least when you do a naive approach of pulling in your dependencies. So NSO TS depends on the NEDs, right? And if all we did was pull in the latest NED, that means we could break things because we could check in broken stuff on the NEDs. Broken as in they still work. They compile and they load locally, but they wouldn't work together with other NEDs or together with our service code. I'm sure you've seen if you use a NED, you've upgraded it, and there are some backwards incompatible changes, and now you have to change your service code to adapt to that, right? So if we were naive, just pull in the latest version, we'd have lots of those problems. We solved this dilemma by doing version pinning. All of you are familiar with version pinning? Everyone is tired. No one is familiar with that. Each commit of one of the NED repositories are going to lead to uniquely identified binary artifacts. So these 3 commits, we compile it, for each time, run a CI pipeline, and then we output binary artifacts, and they're going to be tagged with a version number. We use the CI pipeline ID for that, so it's 123, 130, 131. It's not sequential because the numbers are handed out across the entire GitLab instance. So if you have multiple repositories, they're going to share numbers, right? Then in the NSO TS repository, what we pull in is explicitly version tagged. So here's a list of the NEDs and the corresponding version numbers that they have. You can see that some have rather high numbers. It's 143,912. So you end up with quite a few builds after a while. And now you must think, gosh, what a tedious and boring job to keep this list up to date. And of course it is. And we'll get to how we avoided that in a couple of minutes. Before that, I just want to talk about how we do branches on NEDs and something called rebasing. So from a Git perspective, each NED repo normally has 2 branches. There's the master branch and something called TS. The code committed to master is a representation. Well, it's essentially what we receive from upstream, right? So if Cisco produces a NED, then what we get from there is what we're going to commit to master. Unfortunately, we get zip files, and we have to extract them and put them in a Git repo, but hey, that's just reality, right? So the second branch shown here, TS, short for TerraStream, is a branch where we keep our local changes to the NED. And it was the CI builds from the TS branch that we just looked at. I mentioned before how we wanted a better structure for NEDs, how to avoid certain problems of upgrading NEDs, and this is it. As we saw, the TS branch here, it's based on master, but it can diverge by having more commits. That means local changes. So we have local changes to the NEDs, right? Local changes, you think, is that a good idea? No, it is not. We generally strive not to have them. Maintenance is sort of expensive, and we'd rather have Cisco do this for us. However, reality often forces your hand. So we end up making changes. Maybe we're under time pressure. We have to come up with a solution. We do it ourselves. Sometimes we have beta software running on the routers. We have to make adaptations to make it work with them. So we just end up with having local changes. Whatever can be upstreamed should be upstreamed. So that's our intention at all times, and we strive for the TS branch to be, 0 commits ahead of master. It shouldn't diverge. It should be the same as master. That's the goal that we're always working towards. But we're often in this flux where that's not true, right? I mean, you have a time window from when you've written a local change, you push it upstream, but before it lands on upstream, you have to keep it locally, right? So at the point where a new version is added to master, it will look like this. So the TS branch, you can see how it's still based on an older commit of the master branch, and it has our local changes, right? And then we have the new commit on master, which is a new version released by Cisco. Okay. What we want to do now is move the TS branch so it's based on the latest version of master. And Git makes this magically easy for you through a command called rebase. Rebase will unroll all of those commits on your local branch and then replay them on top of another base commit. This is the result, just like we wanted. All of those commits are moved. And it's this branch structure together with rebase that makes it so easy to keep local changes. So let's say we upstream one of our changes. We send it to Cisco, like the first commit on the TS branch. We take our patch, send an email or whatever way we have sending a patch. New version is made available from Cisco, including our patch. So at this point, TS is still based on the old commit of master, right? And then we're going to rebase it. Rebasing that, Git will see that the changes done in that first commit of the TS branch are not needed because the master branch already contains them. So when you use the new commit on the master branch as our base for the rebase operation, then that first commit in the TS branch will simply disappear. It will be removed because it's not needed anymore. And that is how we move towards 0 commits on the TS branch. This is thus the result. We have, if you saw before, there were 4 commits, right, on the TS branch, and at the end we end up with 3 because it was merged upstream. So, rebasing is often easy. Doing this constantly for new NEDs, and you saw we had a bunch of them. It can be sort of boring, right? So what do we do about that? CI-assisted rebase, of course. So, Cisco releases a zip file. We download the zip file. We put it on master. This is what happens on the master branch. We run those tests. Second stage, which I sort of skipped before, that's what we're going to talk about now, is a rebase job. So this is going to check out itself and then rebase itself and push that back. So we're not doing rebases manually, we're doing them automatically. Here's a list of the CI pipelines. So we can just illustrate how this works, right? You see the one at the bottom here, it's pipeline number 19020. That's on the master branch. And then shortly after that, you can see 19021 on the TS branch. They always come in pairs like this because in the master branch CI pipeline, it rebased TS and then pushed that, which is then, of course, going to trigger a new build of TS. Then the one above that, 19029 on master, it did a rebase, and shortly after 19030, we see on the TS branch, it's doing the CI pipeline. So how do we do these things in CI? It's really quite simple. It's not harder than this. If you look at the end part here, that's the script, just like we had a script before, right? We clone ourselves. There's a convenient environment variable called CI project path available to us. So we clone a copy of ourselves, even though when you're in your CI here, you actually have a checked out copy of yourself already, but don't use that one because it's a shallow copy. So instead do this. do a git clone. Then we cd, we change our directory into that. We do a git checkout of the TS branch. We rebase that on master, and then we push it back. We have the force push because we rebased. Then you have the push, the force push. That's it. That's simple. The magic is really in the setup for this. So above this, in the before script, you can see SSH add there, for example. We're adding in a private key. This is how we authenticate with the GitLab server, right? So that's an environment variable, and you have to fill in your GitLab system. Under settings for the repository, you can fill in secret environment variables. And that's where you put your private key. And then in another place, under settings, you need to fill in a deploy key. That's where you put your public key. You do these two things, and this works. So, you remember this, version pinnings, and how boring, tedious, and repetitive it would be to manually update. What we just looked at was the CI pipeline for the master branch, right? That rebased TS. Looking at the CI pipeline for TS instead, it looks different. Instead of that rebase job at the end, we have a different job that's called git open MR. This, of course, opens a merge request. So what it does, it checks out a copy of the NSO TS repository. It takes that list that we just looked at and updates the line for itself. So I mean, we're in NED UNOS Yang, I think that's the NED. It will update that line and fill in the new version number that it should be used, that it just produced. And then it opens up a merge request. So this is what it looks like on the NSO TS. Unfortunately, I don't have any of these right now, I think. So we're going to have to look at a screenshot from before. Here's one of those merge requests. Robot update NED UNOS Yang 19030. And this is where where it all comes together, right? I mentioned before how multiple multiple repositories create sort of a possibility of breaking things. This fixes it, because when you open up a merge request, when you do a change on the NSO TS repository of explicitly pulling in a certain version, that means that this is going to go through testing on the NSO TS repository. That's our main repo where it's tested. This new version of the NED is tested together with all the other NEDs and together with our service code. So if something breaks in that part, then this is not going to work. The merge request is going to show failed, and you can't merge it. Right? It's that simple. So I mean, to further automate things, you could potentially automatically accept these things, but it's sort of fun, and there's a certain pleasure in watching merge requests being opened up by a little robot and then merging them. It feels good. So we've refrained from automating all of it. Achievements here. Okay, automatic download integration of NEDs. We allow for simple, local NED changes while still making it very easy to update to the latest NED. We do explicit NED version pinning to get around the sort of NED-related failures that you could run into otherwise. Testing code base across multiple. Okay, that's actually coming. So it's sort of CI-assisted automated development here for fun and profit. Just looking at that, what we do here is, if you have a couple of alternatives, different ways of solving something, you typically go with the simple approach. But by using CI as your sort of robot or assistant, you can actually take the sort of cumbersome approach, but automate away the cumbersomeness of that and remain with just the pros, which is what I think we've done here. And I mean, I'm sure you can identify other things in your development process where you can do similar things, right? So just having this as a sort of a generic tool. I'm just showing a couple of examples of what we've done, right? Okay. So next thing then, multiple NSO versions. We've obviously deployed or picked a single NSO version that we're actually using. That's the one we're deploying. And on master, this is, of course, the one that we're using, right? Most of our testing is also using the same version. But improvements are being made to NSO all the time, and we sort of want to move along with that. And so it becomes quite important in testing our code together with other versions of NSO. So we know if these are sort of good candidates for moving to. Something breaks, maybe we need to open up issues so bugs can be fixed. The earlier we do this sort of testing, the better. And like everything else, we turn to CI to help us do this, right? So the NSO version that we use is controlled in a few places. There's like a Docker file that defines which version to use. There's a make file. There's a GitLab CI file. But I think there's 3 places essentially. So it's quite a few places. all the external repos, like we just looked at, they're compiled for multiple versions of NSO, right? So that's sort of the preparation that you need to do to test with multiple versions of NSO. Master branch uses a specific version of NSO, but another branch can use another version. This is exactly what we're doing. We have parallel branches using different versions of NSO, and we can check that all the tests are passing. So here we can see this is a list of the branches on the NSO TS repository. At the bottom, we have the master branch that's running 455, if I remember correctly. And then we have two other branches, NSO 456, which is, of course, NSO 456, and NSO 461. So these two branches are created and maintained automatically. They are rebased every night on master. So you can see they don't diverge very far. It's like 8 commits ahead, 9 commits ahead. If we do need to do some changes that are specific to 461, for example, we can actually commit that thing on that specific branch. There's a script here that automatically opens up a merge request, just like we saw for the other NED repo. It automatically opens up a merge request to start using the new version of NSO. I like this script. It's quite nice. I wrote it. It logs in to the tailf issue tracker, looks at all of the open issues that we have. It then extracts the README file from the new version of NSO, and it cross-references between these. So it says, if you move to this version of NSO, all these issues, which are currently open in the bug tracker for you, will be fixed. That gives you a nice overview of what moving to this particular version will fix for you. Took a little while to put this together. I think it was worth it. Maybe this one I can probably share actually somewhere. I should do that. So here you just have, and these are our actual issues, right? This is the continuation of that. The merge request text is like super long. So not only do we get the links, but it also includes sort of the excerpts from the README on all these individual bug fixes. I'm done soon. Sorry, I'm sort of over time here, but so early on I was sort of trash talking, just doing this sort of comparison with based on text. So we do precisely that. I mean, you've seen already what's the base of our testing, but we also do this sort of simple text comparison. I'll explain why. So we actually have it checked into our Git repository. We have expected output checked in, and that has to line with the actual output coming from the CI test. Coming back to this, right? The third stage here, that's the compare config. This is where this is running. So it's in the test stage, we took some output, we saved it as artifacts. In the compare config one, we're looking at those artifacts and comparing them to the expected one. If anything changes, this means that the compare config job will fail, and it will display a diff of this. And in this picture, there is a failing job. You can see it right there, compare something, something. This branch is for updating the ALU-SR NED version. So of course it breaks for one of the jobs that pertains to Nokia SR OS, which is handled by that NED. Here's a piece of the CI job output where we can see this diff, right? So something in the YAML changed, the no shutdown leaf is now moved to another place, right? That's the diff. Manually updating these expected output files is of course boring and tedious, which is why we've automated it. So like anything else, this will open up a merge request for us. So it says git bot update expected output for example config SROS on that branch. And this is what it wants to change, right? So it wants to move, you can see there the no shutdown on the left wants to move up there on the right side. And this means that any change in the configuration output of NCS becomes very explicit to you. So I think this is a very nice thing to have. I think I'm going to stop there. Questions?
Any questions?
So do you have tests? So you're doing all this development and you go along, and do you have tests that you can upgrade from what you're currently running in production to what you've sort of built in your final stages there?
Upgrading as in?
As in loading your new package. So, I mean, presumably your build builds your new packages, And so you want to make sure that when you load that into your production system, all your instances are still there and everything works.
Right. We're getting there. We've started looking at this, right? So we have CDB upgrade code. So when we're doing changes to the Yang models, right, and you need to move around data, we're writing code. So in this, you know this better than I, but you start up CDB, you have different phases, and you have the opportunity to have the old data and the new data, and you can do transformations in between, right? So we want to test that code as well. So there is a testing job for it. Not sure which one. It doesn't matter which one it is. Someone of my colleagues somewhere here should probably be able to help me. But it doesn't matter. So we've started doing this. Is it all covering? No, probably not. Overall, so where I just stopped in this presentation was about deployments, continuous delivery, continuous deployment. We're not really at continuous deployment, but I think we deploy fairly frequently, which means that the steps at every given time we deploy, it's not going to be that much new features, right? So the risk is always kept low. If you do a release a year, that means that you've done a lot of things and the risk increases, right? So we're sort of doing this to keep it down. I'm not sure if that answers the question. Okay, sorry. I'll include it as I'll include 2 more slides here as the answer to this because it's really important. So. We're not doing continuous deployment. Maybe you want or you don't want. It's sort of risky. It feels a little scary to do that, right? I mean, just pushing out a new version. Oh, will it break or not? So one of the things that we are doing to make this a little less scary is to use feature flags. So if you develop new features, you develop it on a branch, right? And at the point where you merge this work into master is also the point where this sort of becomes active. Okay, you need to deploy it too, right? But let's say we have feature branch A and feature branch B. We merge in A, we merge in B, and then we do a deploy of this, which means that both of these new features are going to go live for our users or our services or whatever it is that they're doing, right? Now the problem becomes, what if A is broken? We need to back it out. So do we back it out of Git? How do we do that without backing out B? Do we then do a new redeploy? It's quite sort of cumbersome, becomes big. Now we're just talking about 2 feature branches. Another way would be like, okay, we do a deploy straight from a feature branch to see if that works. But of course, that only works if you want to try one feature branch. If you want to sort of evaluate that over a period of time, you can only do it on A or on B. Or you create yet another branch, which is feature A and B together, and you deploy from that. But that's also sort of cumbersome, right? So this is where feature flags can help you, and we've started doing this. So when we add in features A and B, I stole these slides, by the way. I haven't drawn these. So launch darkly, apparently. Credit to them. When you implement feature A and B, you can add flags around these. So you can enable or disable that feature through a configuration flag. And that means that once you deploy it, it's not magically enabled, but you have the configuration option that you can set later on to enable or disable it. If anything goes wrong, you can just turn it off right then. We're using this to some extent. You can have both global flags for a feature as well as on a per service instance, right? So if you have just that. If you can do it on a per service instance and then slowly do a phased rollout. Yep. I'll put this here as well. Shameless plug.
Thank you very much, Kristian.
Thank you.